Okay, so this today's class will talk about multivariable calculus. This is the other topic which I am going to discuss as part of the preliminaries. Last time I talked a bit about linear algebra. So let's start. Now, so let's just recall the derivative in one variable. So let's say that recall so if I have a function defined on an interval AB, real valued function of one real variable, and suppose P is a number lying in this interval, we say that f is differentiable at P with derivative f prime P if limit h going to 0 f of p plus h minus f of p divided by h equals f prime p. So to say that f is differentiable at p means that this limit exists, and the value of the limit we denote by f prime p, and we call it the derivative of f at p. Now consider f from u to r, where u is in Rn, n greater than or equal to 1, is an open subset. So I have a function defined on an open subset of Rn. Again, I take a point P in U. I take a point P in U. If I just try to imitate the previous definition, the ratio doesn't make sense, because I'll have f of p plus h minus f of p divided by h. Now the point is that this h would be an element of Rn. So while this f of p plus h minus f of p would be an element here, so I can't divide by an element of Rn. So this ratio doesn't make sense. So instead, this will not work. The difference quotient concept will not work. So let us rewrite. Let's go back to the one variable case and rewrite the equation for a derivative, the definition for a derivative, in a different way, which will easily generalize to higher dimensions. Let's rewrite the one variable derivative. So I'll rewrite it as follows. So I'll just write, well, first to say that limit h going to 0 f of p plus h minus f of p divided by h equals f prime p is the same thing as saying that limit h going to 0 f of p plus h minus f of p minus f prime p times h divided by h equals 0. All I have done is I multiplied and divided this f prime p by h by h, and then that's just 1, and then brought it to this side. And even this is not good enough. Notice that to say that a number limit of this is equal to 0 is the same thing as saying limit of the absolute value is 0. So now the point about rewriting the original derivative definition this way is that this can be generalized to higher dimensions. So as I was saying, this works for n greater than or equal to 2. Here n is of course the dimension of the domain. So what we have to observe is that this function h going to f prime p times h is a linear map from R to R. So this is just multiplication by multiplication of any h by this fixed number f prime p. So in higher dimensions, so what I'll do is, motivated by this, by these observations, we say that f from here of course this works for n greater than or equal to 2. Observe that h going to f prime p is a linear map from R to R. This is in the one variable case. We say that f from this to R is differentiable at p if there is a linear map L from Rn to R such that f of p plus h minus f of p minus LH norm absolute value of this divided by norm h limit h going to 0 is equal to 0. So this is entirely motivated by this previous equation. This in the one variable case L of h, the linear map, is as observed here. It's just L of h is f prime p times h. In general, we define it like this. And of course, in the one variable case, this that linear map is essentially the derivative. And similarly here, we say that the linear map is the so we say that if we say it's differentiable if there is a linear map, and we would like to say that this linear map is we would like to call this linear map the derivative of f at p. The only thing is that it's not quite clear at this stage that whether there's a unique linear map. In fact, that is true. It's a small proposition. If such a linear map exists, then it is unique. In other words, if there are two linear maps L1 and L2 for both of which this equation holds, then one can show that L1 equals L2. Once we know it's unique, we can call it the derivative. definition, L is said to be the derivative also called the Frechet derivative of f at P. So in short, the derivative in higher dimensions is going to be a linear map. Well, this was for the case of a function from Rn to R. It's easy to generalize this to Rn to Rm. Now consider f from U to Rm. Again, as before, U is a open set in Rn, and the target instead of being R is another Euclidean space Rm. Well, there are two ways at this stage. There are two ways of defining differentiability of f at P. Let P belongs to U, belong to U. We say that f is differentiable at P if one of the following equivalent conditions holds. I can just generalize the previous definition. So there is a linear map L from Rn to Rm such that limit h going to 0. Now instead of absolute value, I have to use the norm sign. So limit of f of p plus h minus f of p minus LH divided by norm h equal to 0. So this is a direct generalization of this the previous one where I had an absolute value sign. Or the other thing is, since f is a map whose image is Rm, I can write, if we write f as f1 fm if we write f in terms of its component functions, then each fi is differentiable at P. Note that fi would be a function from an open set in Rm into R, so which was the case we had dealt with earlier. So these two are equivalent. In the first definition, we also have the the definition of the derivative as well. I mean, this condition says it's differentiable, but the derivative is actually a linear map from Rn to Rm. Second condition, I'm just mentioning the differentiability part. I'm not saying what the derivative actually is, but it's easy to see that this L, which is the derivative, is related to, if I look at it in terms of components, it's just the components of L are basically derivative of this and derivative of f1, derivative of f2, etc. So I might as well write that. Before I do that, let me just, so this L, we denote L by df at P, or sometimes capital Df subscript P. So one would like to, so this notion of differentiability derivative as a linear map is actually quite strong, but fortunately it's related to the classical notion of existence of partial derivatives by the following proposition. So again, let f from u to Rm and P belongs to u. If del f I by del x j, I varying between 1 and m, so f1, f2, fn, as before they are component functions of f, and j varying between 1 and n. If these partial derivatives exist, now it's not enough that they exist only at P. So we want something stronger than that actually. So if the partial derivatives exist in a neighborhood of P, not only should they exist in a neighborhood, and they are continuous there, then f is differentiable at P. And of course, in fact, if we write, rather than saying if we write, let me say that the matrix of df at P, remember that this is a linear transformation, so therefore I have a matrix of this. Now the matrix of a linear transformation is well defined when we fix a basis for the domain vector space and the target vector space. Here we will take the standard basis. So in fact the matrix of DFP with respect to the standard basis of R n and R m is given by so I'll use this square brackets to denote the matrix of this linear transformation. So this is given by the ijth entry of this matrix is del f I by del xj. Is given by this. So in short, if you know that the partial derivatives exist at in a neighborhood of a point and are continuous in that neighborhood, then f is differentiable in our sense, Frechet differentiable, and matrix of df as a linear map is given in terms of the partial derivatives. So this matrix is also referred to as the Jacobian matrix. So the matrix, this matrix is called the Jacobian matrix of f at P. Now, so let's move one step further. Let's just observe that this partial derivative is a special case of something called the directional derivatives. So let's talk a bit about that. This is going to be important later on. So directional derivatives. So after all, what is the, recall the definition of partial derivatives of a function f from u to real valued function defined on an open subset of Rn. Well, so as usual, I'll take a point P in U. So this U is in Rn. So for each direction in Rn, I have the partial derivative. So del f by del xi at P. So this is by definition the limit h going to 0, rather than h going to 0, let me just write it in a different way. Limit t going to 0, f of p plus t ei minus f of p divided by t. So this is the, I mean, of course, assuming that this limit exists. If this limit exists, we say that this is the ith partial derivative of f at P. Now, this, what is this ei? Well, ei is the standard basis. Here E1 equals 1, 0, 0. En equals 0, 0, 0, 1 is the standard basis of Rn. And what I have written here, f of p plus t ei is the same thing as f of, so if p1 dot dot dot, so in the ith spot pi plus t, so I will be just adding t, the others remain unchanged, where p is p1 pn. So I just rewrote this, whatever I wrote here, in more familiar, perhaps more familiar notation. So all I'm doing is I'm just adding t here to the ith coordinate, and then dividing by t and taking the limit. So this is our usual definition of partial derivative. Nothing new going on here. But what I would like to point out is that if I write it in this form, what I have done here, as I can easily generalize, there is nothing special about this EI. Now let's take any vector v in Rn. If the limit t going to 0, so all I do is, instead of EI, I'll just replace it with a v, this v. So I'll look at p plus tv minus f of p divided by t. If this limit exists, then we call it the directional derivative of f along v at p, and denote it by v of f. So I might sometimes actually in this notation the subscript p is not the point p is not making an appearance. Ideally it should, but when we, in the context that I'm going to be talking about it, it will not be necessary to refer to the point p. So let me just leave it like this, and just observe that if I take v to be an element of the standard basis, then I recover partial derivatives. Observe that EI of f in this notation is just del f by del xi at p. So this is a direct generalization of a partial derivative, the notion of a directional derivative. Now there is a very clear way of interpreting this. So let us look at this note that t going to p plus tv, well, this is a parameterization of the straight line passing through P in the direction V. In other words, I have a P, I have a V. So this straight line is as t varies from goes from minus infinity to infinity, I get the entire straight line in Rn in this direction. So with this topic, so we'll end this lecture here and get back for the next lecture.